Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the atomic radius. Today we are going to study a topic that's atomic radius. So what do we mean by this term? First of all, an atom is assumed to be spherical in shape, and thus the size of an atom is generally given in terms of the radius of that sphere and is termed as atomic radius. So what exactly this line is saying, that we have assumed our atom to be in the shape of sphere and the radius of that sphere will be taken as the atomic radius. Now it is usually defined as, the atomic radius is defined as distance between the center of the nucleus and the outermost shell where the electron is present is called the atomic radius. Let me make you a diagram. Just assume that this is the nucleus of the atom. Assume this is the first shell, the second shell, the third shell, and so on. Now let's consider this third shell is the valence shell. So the distance between the center of nucleus to the valence shell will be termed as the atomic radius. Atomic radius. Now, next points. The exact measure of atomic radius is not easy due to the following reasons. The very first reason, the atom does not have a well-defined boundary. The atoms does not have any well-defined boundary, due to which measure of the exact radius is not possible. Now the second point, it is not possible to get an isolated atom. Now the very third point, the size of an atom is very small, of the order of about 10 to the minus 10 meter. It is very small quantity to measure. So these are the 3 points due to which the exact atomic radius is not specified. It's not measured. So what next? So an estimate of size of an atom can however be made by knowing the distance between the two atoms in the combined state. That is, the bond length of the molecule having only one sigma bond or a single bond. Now, the bond lengths are generally measured by the techniques such as the X-ray diffraction, electron diffraction, infrared spectroscopy also known as IRS, and a nuclear magnetic resonance known as NMR. So let's talk about the different types of atomic radii. After that, I will make you understand how to evaluate the radii by knowing the bond length. First of all, there are three types of radii. The first one is the covalent radius, the second one is the crystal radius, and the third one is the van der Waals radius. Now let's talk about the covalent radius. Covalent radius is defined as half of the distance between the two nuclei of two like atoms. Two like atoms means H2, Br2, I2, Cl2, N2, O2. But they must be bonded together by only a single bond. That means Cl2, Br2, Y2, but not O2 because having two bonds, not N2 is having three bonds. So let me make you understand this thing first. Now let's talk about the Cl2 molecule. I am talking about this Cl2 molecule. We know that chlorine forms the single bond with chlorine. So this is the bond length. What we have to do, we have to divide the bond length by 2. That is, we have to take the half of the bond length, and we will take this half bond length to be the atomic radius of chlorine. Atomic radius of chlorine, that is equal to the half of the bond length. Now, now let's talk about the crystal radius. The crystal radius is for metals. Crystal radius, it is defined as one half of the distance between the nuclei of the two adjacent metal atoms in a crystal lattice. Let's take an example. I'm taking the example of copper. Now, assume this is the first copper atom and this is the second copper atom. What we have to take? We have to take their nuclei, then we have to take their internuclear distance. After that, we have to divide that internuclear distance by 2 to get the radius of the copper atom or any metal atom. So, I'm writing crystal radius of copper atom will be equal to the half into internuclear distance. Now let's talk about the van der Waals radius, the third one. Van der Waals radius, it is half of the distance between the nuclei of the two non-bonded neighboring atoms or molecules of two adjacent molecules. Now let me take an example. Now I'm going to evaluate the van der Waals radii of Cl2 gas. Now this is the first chlorine molecule and this is the another chlorine molecule. Now we have to take the distance between the nuclei of two non-bonded neighboring atom. That means I'm going to take the distance of nuclei between this chlorine and this chlorine because they are non-bonded to each other. Now what we have to do, we have to take their internuclear distance and then we have to divide this by 1 by 2 to get the van der Waals radii. So van der Waals radii are comparatively very large comparatively to the crystal radius and the covalent radius. I hope you got the van der Waals radii. I'm marking it again that it is the half of the distance between the nuclei of two non-bonded neighboring atoms. Non-bonded neighboring atoms, I have taken this chlorine and this chlorine. Of the two adjacent molecules, the molecules we have taken the Cl2, the first Cl2 and this second Cl2. So the distance between the nuclei of two non-bonded atoms of the neighboring molecules is called the van der Waals radii. Now let's talk about the increasing or decreasing order of the radii. I have already told you that van der Waals radii is the greatest one, then second comes out of the crystal radius, then the lowest value is of the covalent radius. So now let's discuss the trends of the radius in a group or a period. Here I am writing trends of atomic radius in groups and periods of periodic table. Now firstly let me give you some points. The atomic radius of any element, the atomic radius of any element is inversely proportional to the effective nuclear charge. As the effective nuclear charge will increase, The attractive pull of the nucleus for the outermost electron will increase, thereby decreasing the atomic radius. So what I have said, if the effective nuclear charge increase, then the atomic radius will decrease. Or we can say it in a reverse fashion. If effective nuclear charge decrease, if it decrease, then the atomic radius will increase. I hope you got this point. Now let me talk me some another point. The atomic radius. Atomic radius is directly proportional to the screening, or we can say shielding effect. As the screening effect or a shielding effect will increase, the outermost electron will feel less effective nuclear charge, thereby increasing the atomic radius. So what I have said, if the screening effect increase, then atomic radius also increase. Or we can also say that if the screening effect decrease, then atomic radius will also decrease. Now let's talk about the atomic radius in group. I'm writing trend of atomic radius in groups. Let me take an example of group number 1. I'm talking about group number 1. It's hydrogen, lithium, sodium, potassium, rubidium, cesium, and finally the francium. Now here, as we move down the group, I'm writing, as we move down the group, as we move down the group, what will happen? The number of shells will increase. Number of shells will increase. Then what will happen? Thereby increasing the number of electrons in inner shells. In inner shells. Then what will happen? Then screening effect will increase. Screening effect will increase. But down the group, effective nuclear charge must increase, because down the group atomic number is increasing, so the number of protons is also increasing. Then if nuclear charge also must increase, then what is happening actually? What is happening actually? Screening effect surpasses is the increasing nuclear charge. Thereby what will happen? The outermost electron will not feel the effective nuclear charge, due to which the size of the atom will increase down the group. The size of atom, or we can say atomic radius will increase down the group, Now hydrogen belongs to the period number 1. That means here we are having only one shell. In lithium we are having two shells. In sodium we are having three shells. In potassium we are having the four shells. Rubidium five shells. Cesium 6 shells. Finally the francium 7 shells. As we are moving down the group, the number of shells is increasing. If the number of shells is increasing, that means the outermost electrons are going far away from the nucleus. Moreover, the shielding effect or the screening effect will also increase, due to which the size of an element will increase from top to bottom in a specific group. And this rule will be applied to all the groups of the periodic table. So I hope you got this point, the trend of atomic radius in the groups. Now let's talk about the trend of atomic radius in a period. Now let's talk about trend of atomic radius in a period. Let me take an example of period number 2. The period number 2 starts from lithium, then beryllium, then boron, carbon, nitrogen, oxygen, fluorine, and finally neon. So what will happen? As we move across a period, that is from left to right, when we are going from left to right, I'm writing, as we move across a period, that is from left to right, then what will happen? The shell number remains the same. The shell number remains the same, and one electron and proton is increasing each successive member. So as we move from left to right, the shell number will remain the same, but one electron and proton is increasing by each successive member, due to which what will happen, my dear students, what will happen? The effective nuclear charge will increase. The effective nuclear charge will increase. What does that mean? As the effective nuclear charge will increase, the attractive force of nucleus for the valence electron will increase, thereby decreasing the atomic radius. Thereby decreasing the atomic radius. Thereby decreasing the atomic radius across the period. So what we got in this lecture, that the atomic radius increased down the group, and the atomic radius increased down the group, and the atomic radius decrease across a period. That is, atomic radius increase down the group and atomic radius decrease across a period. Now let me show you one thing. Here you can easily observe that. What we can observe that, let's talk about the group number 1. Here, as we are moving down the group, the atomic radius of the elements are increasing. Here you can easily observe this thing. Let's talk about the group number 13. Here you can also see that the atomic radius is increasing down the group. Why it's increasing? Because down the group number of shells are increasing, the screening effect is increasing, due to which the size or the atomic radius of element is increasing. Now let's talk about the period. In period, let's take the example of period number 2. As we are moving from left to right in a period number 2, the atomic radius of elements are decreasing because the shell number remain the same, but effective nuclear charge is increasing because the proton is increasing with each successive member, due to which effective nuclear charge is increasing, thereby size is decreasing. Here you can also observe that in the period number 4 you can see that the atomic radius of the element is decreasing with each successive member as effective nuclear charge is increasing. So I hope you all understood today's lecture. That's all for today. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.